Hey guys, today we're going to be talking about our molecular orbital theory, and by the end of this video you should be able to talk about bonding and anti-bonding molecular orbitals. You should understand where they come from, how the overlap of atomic orbitals leads to the formation of bonding and anti-bonding orbitals, and how those orbitals, how their filling is going to either stabilize or destabilize our molecule. We should also be able to form period 2 diatomics, either heteronuclear or homonuclear, so either one atom type or two atom types, and you should be able to draw their molecular orbital energy level diagram. Once you've drawn that, you should also be able to correctly place electrons within there, and from your filled diagram, determine the bond order. And within our molecular orbital description of a molecule, we should be able to correlate it with bond order, bond strength, bond length, and magnetic properties of that molecule. So molecular orbital theory is a theory that was developed because of the failing of other theories. For instance, our valence bond theory, or VB theory, it fails to explain a molecule's excited state. So what energies we're looking at when we're thinking about a molecule's excited state. Okay. So it's a more sophisticated model used to describe the orbitals within a molecule. So our molecular orbital theory, which we call MO, more sophisticated. And instead of looking at atomic orbitals, it uses the idea of molecular orbitals. So it talks about the entire molecule, not just individual bonds. Okay? So it again is a mathematical operation where we combine the energies of our atomic orbitals to get the shape and energy of the molecular orbitals. Okay. So we still have the same rules applied as we do with atomic orbitals, where we follow Hund's rule, we follow Pauli exclusion principle, and the whole idea of atomic orbitals in, molecular orbitals out also applies. So our molecular orbitals still follow the rules. Specifically Hund's rule and Pauli exclusion principle. And still atomic orbitals in equals molecular orbitals out. Okay, so it's kind of like our hybridization in that way. And it's also there to explain what we see experimentally. Okay, so our atomic orbitals, that's atoms only. Molecular orbitals, that's the entire molecule. So when we combined these atomic orbitals to produce these molecular orbitals, we're going to produce two atomic orbitals, where one is lower in energy, one is higher in energy. So orbital overlap. When two atomic orbitals are combined or overlapped in MO theory, two molecular orbitals are produced, one with lower energy, one with higher energy. We call the one that's lower in energy the bonding molecular orbital, the one that's higher in energy the anti-bonding molecular orbital. So anytime we put electrons into a bonding orbital, it stabilizes our molecule. Anytime we put electrons into an anti-bonding orbital, it destabilizes. So let's look at the molecular orbital diagram for hydrogen. So first, let's look at our energy here. Before we bond, we have two atomic s orbitals for hydrogen. Okay, they're separated and we combine them. And we're going to take and produce a bonding molecular orbital and an anti-bonding molecular orbital. So basically what happens is we add the wave functions of our 1s orbitals to produce our bonding molecular orbital. For our H2 molecule. So this is a molecular orbital that describes the molecule. And it's a sigma 1s molecular orbital. Then our other is when we're subtracting our 1s. So subtracting wave functions, and this produces a node. So that area of no electron density, and putting electrons in there is going to have a destabilizing effect. So that node is produced when we have that anti-bonding molecular orbital. And we call this a sigma star 1s. Okay, so we've got our bonding, that's sigma, and then anti-bonding sigma star. Let me just line that up so it looks a little bit better. There we go. Okay, so those are our two types of orbitals that are produced when we overlap two s orbitals with overlap. Okay, so we've got our bonding and our anti-bonding. So we would say that our bonding orbital is a constructive combination of atomic orbitals. So they're going to be lower in energy than the atomic orbitals. At least usually. If we're combining two orbitals that have different energies, they might not be lower in energy than both atomic orbitals. And then our antibonding orbitals. This is a destructive combination of atomic orbitals. This is going to be higher in energy. This is going to produce a node. No, so that area of no electron density. Between the two nuclei. So essentially, if you put electrons into that antibonding orbital, there's going to be no electron density between the two nuclei, which destabilizes. Okay. Okay. So let's just look at some terminology associated with this. We have what's called a sigma bonding orbital. And that's going to be our direct overlap between two nuclei. So when electron density is shared between two nuclei, so this could be the direct overlap of two s orbitals, the direct overlap between an s and a p orbital, or the direct overlap between two pz orbitals. And it's two pz orbitals because those are the ones along the inner nuclear axis. Then we have sigma star. Anti-bonding orbital. Okay, so this is when we have a node between two nuclei. Now, we do not have to have direct overlap, just like we saw with VB theory. We can have indirect overlap. So if we have a pi bonding orbitals, or bonding orbital, this is when we have the indirect overlap of two py or px orbitals. Okay, and then if we have a bonding, we have to have an anti-bonding. So we have our pi star. So that's anti-bonding orbital. So produce a node. Okay. So how do these occur? Let's look at this a little bit, but in the way of like phases of our atomic and molecular orbitals. Okay, so if we think about a sine wave, like so, we have a negative phase and a positive phase. Okay, if we have something like an s orbital, so if we're thinking about it in terms of x, y, and z, if we were to look at its wave function, it would look like this, where we don't have any negative phase. And no node. Of course, if we go on to a 2s orbital, we will get that one node in there. If we look at a pz orbital, like so, we would get something that looks like this, where we have a negative phase and a positive phase with a node in between them. Okay, so that would equate to that. That would equate to that. So our different lobes are in different phases. So our lobes are going to have alternating negative and positive phases. And if we think about our dxy orbital, for instance, they are also going to have alternating lobes. So I'm not even going to try and draw the wave function, but they're going to have alternating positive and negatives like we see here. Our positive and negative phases. I am so good at coloring in the lines. There we go. So when we think about combining, the phase matters. So if we combine and the phases match up, we have constructive combination. If we combine and the phases do not match up, we have destructive combination. So thinking about taking something like this plus let's just go ahead, something like this, and then combine it with something like this. And we produce something like this. Fantastic, a constructive combination. If instead we combine something like this with something like this, we will have destructive combination, and it'll just leave us with a destabilizing effect. So our constructive combination, this plus this, produces this. Destructive, this plus this, produces our node. Like so. So this will be our sigma star, and this will be our sigma. We can look at this mathematically by looking at what's called our bond order. We can look at this method bond order. Our bond order gives the stabilization and type of bond between two atoms. If a bond order equal to 0, there's going to be no bond between those atoms. Okay? If we have a bond order equal to 1, we'll have a single bond between the two atoms. Bond order equal to 2, we will have a double bond between the two atoms. Well, a bond order equal to 3, or a triple bond between the two atoms. Okay? We solve for our bond order by taking our number of electrons in our bonding orbital minus our number of electrons in our anti-bonding orbital. We take that whole thing and we divide it by 2. So in the case of hydrogen, if we go up to hydrogen, hydrogen will have a bond order of 1. So let's look at what that would look like with our molecular orbital diagram. So molecular orbital diagram, we have 1s atomic orbital for each of our hydrogens. And then those are going to combine to produce a bonding and an anti-bonding molecular orbital, roughly averaged between the two. And we'll have both of our electrons in the bonding orbital, none in the anti-bonding orbital, because we only have two electrons that are both going to go into the lower orbital or energy orbital. When we solve for our bond order here, this would be 2 minus 0 divided by 2, which gives us 1. We can do the same thing for helium. So if we want to look at He2 rather, we take our 2 1s orbitals of helium, combine them, producing our our bonding, sigma. Then our anti-bonding, sigma star. And here we have 4 electrons, so we put 2 here, giving us a bond order of 0. So it's going to be a molecule that does not exist. So He2 does not exist, which hopefully we know. We can, if we looked at He2 2+, we could actually get a molecule here. And let me show you. He2 2+, we are missing an electron from each helium. And it'll have the same bond order that we see in hydrogen. Because we've lost those 2 electrons. So He2 2+ has a bond order equal to 1. So it will actually produce a bond. So that's how we use molecular orbital theory to predict if it'll produce a bond. We call this combination of those atomic orbitals the linear combination of atomic orbitals. So what we do in order to produce these molecular orbitals is a linear combination of atomic orbitals, or LCAO. So the overlap of atomic orbitals to produce molecular orbitals in MO theory is called the linear combination of atomic orbitals. Okay? To produce a sigma orbital, we overlap an s orbital from atom A with an s orbital from atom B, or s orbital from atom A and p orbital from atom B, or p orbital from atom A with p orbital from atom B. The p orbitals just have to be perpendicular to each other, so they have to overlap directly. To produce a pi bond, or a pi molecular orbital, we have to have the p orbital of molecule A, or atom A, with the p orbital from atom B. Those have to be parallel to each other. And these are our bonding linear combination of atomic orbitals. our antibonding. So to produce our sigma star, we have to subtract those linear or those atomic orbitals. So Sa minus Sb or Sa minus Pb or Pa minus Pb. So a subtraction of atomic orbitals, where our pi star, Pa minus Pb when they are parallel to each other. So these are our antibonding orbitals. So antibonding linear combination of atomic orbitals. So we will always have a bonding plus an antibonding when we combine those atomic orbitals. Just when we're combining, it's either an addition process or it is a subtraction process. Okay, next thing I want to talk about is the idea of HOMO and LUMO. HOMO is the highest occupied molecular orbital. LUMO is the lowest unoccupied molecular orbital. What we have, HOMO and LUMO, that's something we can actually determine using molecular orbital theory. And this is one of the things that really makes molecular orbital diagrams shine, is looking at that energy and determining what type of excitation properties you can have within a molecule. So we look at our HOMO-LUMO gap to get information about our excited state. So our HOMO-LUMO gap is the minimum energy required to excite an electron from a molecule or in a molecule from a lower energy state to a higher energy state. So getting that information about the excited state using our molecular orbital diagram. If we see a substance and this substance is colored, that means it's going to absorb light in the visible region. So if a substance has a color, that means it will absorb light in the visible region. So that means that it has a HOMO-LUMO gap that's equivalent in energy to the visible region. Okay? If we see a color, it doesn't absorb that color. So the color we see, that molecule doesn't absorb that color. Rather, it reflects that color. Okay? If a substance absorbs all light, it's going to appear black. And then if it reflects all colors, it's going to be white. So if it's going to absorb UV radiation, for instance. Okay. So our homoluminal will tell us information about what that energy is that it absorbs. Okay, let's look at our MO diagrams for period 2 diatomics. Okay, so when we have a uh, period 2 diatomics that produce a molecule, we look at molecular orbitals. So keep in mind, when we're thinking about our period 2 diatomics, we're going to have atomic orbitals combining in the most efficient way with other atomic orbitals. So they're going to want to combine with atomic orbitals of similar energy. That will give us better overlap, and when we have better overlap, we're going to have MOs with lower energy bond and then higher energy antibonding. So better overlap. Our bonding MOs are lower in energy. And then our antibonding MOs are higher in energy. Okay? And our best overlap is going to come from direct overlap. So our sigma and sigma stars, or sigma, will produce an overlap, so most effective. And on overlap of atomic orbitals. So it's going to have a significantly lower bonding orbital and higher antibonding MO. So those sigma bonds are going to have a bigger gap in energy between the bonding and the antibonding versus our indirect overlap, our pies. So indirect overlap, less efficient overlap, not as great of a lowering of the bonding, raising up the antibonding. Okay. So the gap between the bonding and the antibonding is going to be significantly less. So let's look at what happens between our different types of overlap. So if we've already looked at SF, but look at what happens as we combine 2p orbitals. So our end-on overlap is 2p orbitals overlapping. Okay. So we have something that looks like this. Our 2p z orbitals overlap to produce our antibonding and bonding. So we'll have something that looks like this. So this is going to be our sigma. And then we'll have our antibonding with our node in between. That looks like this. This energy is going to be fairly significant, this difference in energy between the two. If we have our sideways overlap, so 2px overlapping with another 2px, the energy is going to be as great. We get our bonding, which remember, our electron density is above and below the internuclear axis, not right around it, and we get a node. Like that. This is going to be our pi star, 2p, and then just our pi, 2p. And then combining our 2py orbitals. Again, we don't get as big of a lowering of our bonding or raising of our antibonding. Then we get something that looks like this right here. Like so. Okay, so let's look at some MO diagrams for some different molecules in period 2. So let's look at Li2 and Li2 has 1s and 2s. Has no p's. Like something like this. Like that, giving us a bond order of 1. You can also look at Be2. It's going to look very similar. 1s and our 2s. Difference here is we have one extra electron. And this is, sorry, I forgot to put, this is Be, Be, Li, Li. And here, since we have that extra electron, we get a bond order equal to 0. So this will not produce anything. Okay. When we move on, we bring in our p orbitals. Generally, what we would get, where we have our 1s overlaps, and then our 2s overlaps. Just write that a little bit better. And then we have our 3p's. I have one that is sigma, and then two that are pi, like so. So we have our sigma 2p, pi 2p, pi star 2p, sigma star 2p. And we see with our direct overlap, we're going to have a greater difference in those energies. And this is the overall kind of diagram you should see for most period 2 diatomics. There are, however, a couple of snafus in here. So when we have 2s and 2p interacting with each other, this is going to cause additional overlap, and that additional overlap is going to cause a splitting of the energy. So 2s and 2p orbitals overlap a bit for some of the 2p diatomics. Okay? So when that occurs, when sigma 2s overlaps with sigma 2p, so the already formed orbitals, when they overlap, this interaction causes energy splitting. Okay, so what happens is our sigma 2p goes higher to energy, sigma 2s goes lower in energy. That's all due to overlap between those orbitals. So you'll see a little bit of this going on, and it causes the splitting. So we only see it for the atoms at the beginning of the periodic table. Boron 2, carbon 2, nitrogen 2. We do not see it with oxygen 2, fluorine 2, or neon 2, because those are much smaller, so they don't have that overlap occurring. Remember that those are the ones where we pull our electron because of electronegativity. So there is not that interaction between the 2s and the 2p going on with O2, F2, and Ne2. Of course, Ne2 has a bond order of 0, so it doesn't matter anyways. But we will get for O2, F2, and Ne2, this will behave like we expect it, where we have our 2s, sigma 2s, rather, and then we have our sigma star 2s, and then our sigma 2p, and our pi 2p. Our larger, earlier period elements, or diatomics. These two will interact, and this will shift up in energy, this will shift down in energy. And what we get for C or B2 and N2 is a lowering of that sigma 2s. Our sigma star doesn't do anything. Then our next thing is our pi 2p, and above that in energy will be that sigma 2p. So basically a shifting of these two right here. So these are going to switch places. This is going to lower in energy. Okay. So just keep that in mind, that those are going to flip. When we talk about O2, F2, and Ne2, they will be correct, but B2, C2, and N2 will have a flipped order of those. This is kind of a summary of things that are going on with our period 2 diatomics. So B2, C2, and N2 are going to have large 2s2p interactions. So because of that, they're going to have energy reordering, or orbital energy reordering. B2 has a bond order of 1. C2 has a bond order of 2. And N2 has a bond order of 3. Our other ones have, so O2, F2, and Ne2 have small 2s2p interactions. So they will not have energy reordering. And what we get here, O2 has a bond order of 2. F2 has a bond order of 1. And Ne2 has a bond order of 0, so it does not produce a bond. Okay. Next part, I'm going to talk about the idea of magnetism within a molecule due to the way the electrons pair or lack of pairing in the MO diagram. So if a material can be magnetized, it has to have at least one unpaired electron in its MO diagram. So for a molecule to be able to be magnetized, it has to have at least one unpaired electron in its MO diagram. So that electron, that spin, can basically align with the magnetic field. So this allows for the molecule to exhibit an overall spin. We're not canceling out the spin with another electron. And that spin can align with the magnetic field. Okay, so that's something that's called paramagnetic. So these are paramagnetic species. If we do not have any unpaired electrons in the MO, we do not have an overall spin, and it cannot be magnetized. We call this diamagnetic. And there are several of our period 2 diatomics that are, in fact, paramagnetic, and we'll look at one of them. But let's look at what happens when we have a paramagnetic and a diamagnetic material and we introduce it to a magnetic field. So we have a magnetic field balance, which we call a GUI balance. So it basically looks at the weight of something taking into account its magnetism. So if we have a sample, it's going to have a set weight. Right, so it's got a set weight based on how much of that sample you have. Right. There's our balance. If you were to take and introduce that sample to a magnetic field, one of two things will happen. So either it's going to be pushed up by the magnetic field, making it appear like it weighs less, or it is going to be pulled into the magnetic field, making it appear as though it weighs more. That's kind of the basis of a GUI balance. It looks at how much a substance weighs and then how much it weighs after the magnetic field is introduced at a specific magnitude. If, when introduced to a magnetic field, it is going to weigh less because it is weakly repelling that magnetic field, this is a diamagnetic species. So diamagnetic species are going to weigh less in a magnetic field. Our paramagnetic species are going to be pulled in by the magnetic field, so they're going to appear to weigh more. And one of the paramagnetic species in our period 2 diatomics is O2. So O2 is paramagnetic. And I'm just going to write out the MO diagram for O2 so you can see what I mean by that unpaired electron. So I'm going to start out with 2s. I'm not even going to mess with the core electrons. So we have our 2s. Orbitals overlapping, and then our 2p orbitals. And remember, with O2, we don't have the sp interactions, so they're going to behave exactly like we'd expect. We're not going to have a raising of that 2p, the sigma 2p, or lowering of the sigma 2s. Let me just write that a little bit better. Okay. Okay, so this is what it would look like, and we'd put our electrons in. Like so, and then we'd fill up our diagram like this. And as you hopefully can see, we have two unpaired electrons because of Pauli exclusion principle and our Hund's rule, so pair species. Very last thing we're going to talk about in here, finally, is a heteronuclear diatomic molecule. So here we have two different types of atoms. So they're going to give different MO diagrams because of that. So some things you find are bonding orbitals are going to lower energy atomic orbitals, while the anti-bonding orbitals will resemble the higher energy atomic orbitals. Okay, and as a note, our lower electronegativity atom is going to have a higher energy. So let's look at NO. So we have nitrogen and oxygen combining. And we're, again, just going to look at our valence here. So our 2s is going to be higher in energy for nitrogen versus oxygen, because oxygen is more electronegative. So when we combine these, the lower energy orbital will be closer in energy to the lower energy atomic orbital. So our bonding will be very close in energy to our lower energy atom, and our anti-bonding will be closer in energy to our higher energy orbital, giving us our sigma 2s and sigma star 2s. And then we've got our p orbitals. We've got our 2p. They're going to overlap. We'll not have that sp interaction here. Sorry, one second. There we go. Not perfect, but let me actually just a little bit. Okay, there we go. Something like that. Again, not an artist. Then we put our electrons in. We have 6 electrons for oxygen, and then 5 for nitrogen. So giving us a total of 11 electrons. And that is what we end up having. Like so. And that is finally everything. Bye, guys.